Go ahead and get started. Again, thanks for joining us today. I know your time is precious, so we'll go ahead and get started with this. There's a lot of information here to cover. We got a great presentation today discussing the components to make up the thermal envelope and then taking a dive into defining that boundary, including the air barrier and the insulation portions of that. But first, a little bit of housekeeping. Today's presentation is being recorded and it will be shortly uploaded into our YouTube channel. You can find the link to our channel at eepartnership.org/resources. Again, that's eepartnership.org/resources. There you can browse webinar archives. You can look for previous energy webinars that we've had. Also, there's webinars on our City Efficiency Leadership Council. So that's where Sean Acklin and her guests actually discuss the challenges of local governments when tackling current energy management and future energy projects. Their members include, but not limited to, cities, school districts, and other public entities, and is sponsored by SECO. So shortly after today's webinar, you will receive a survey email from Kathy Lawrence. Be sure to fill that out and submit it to receive your course completion certificate that will contain the ICC course ID number that you'll need when reporting your CEUs to ICC. There is a minimum limit of at least 70% of the time of the webinar that you must be present in order to receive the course completion certificate. I understand that people are busy. If you have to leave, unfortunately, if you haven't met that time limit, you don't receive course completion certification. Lastly, the chat and the Q&A boxes are open. Please feel free to post a question at any time during the presentation, and I'll answer them at the end of this presentation. I'd like this to be an open discussion, but there is a time limit. We've got some information to get to, so we will get started with this now. So today's agenda, we've got a little bit of building science that we're going to run through, what makes up the thermal envelope, defining that thermal envelope. Okay, and again, that includes air barriers, what makes up the air barrier, what type of air barriers we've seen, proper installation practices, points of failure, testing of the air barrier, and then on the insulation side of that, we got what is insulation, which is kind of elementary, what types of insulation we see out there, proper installation practices, and also what happens when it's poorly installed. A little bit about me. I've actually started out as a Trek apprentice inspector. I worked part-time as a low volt contractor. I actually attained a associate's degree with residential building performance based on code itself. Spent the last 10 years as an energy rater and field supervisor for one of the largest DFW third-party energy verifiers. That team that I've managed as inspected, the time I was there, inspected over 75,000 homes. Still going strong today. I'm certified as BPI IECC residential, a HERS rater and a lead green rater, as well as being a QA for ResNet and lead. So we've got a little bit of a change up before. If you visited the webinars before, we've actually had some survey questions that were pulled up. We have a new way of doing that, so I'm going to start that now. It's going to be a multiple choice question. I'm just going to type that in real quick. The first question we're going to have basically is what code cycle that you're on. I'm going to add these in as choices, and then you can pick the choices there. We'll all show up in real time for the feedback. Hold on one second. I will show this on the screen. All right, you should see one pull up. It gives choices for that. I'm not sure if that's showing up correctly for you guys. No, it probably is not. I apologize. I'll keep going. This is technical difficulties. I'm having to learn part of that as well. So we'll move on with the presentation. My apologies for that. So who is SPEAR? If you guys have joined us before, you realize and know kind of what SPEAR is. SPEAR is a member-based nonprofit whose mission is to accelerate the adoption of energy-efficient products and services when it's geared around code itself. We also advocate for the adoption of latest IECC of the code cycles and assist cities through the adoption process. So SPEAR is one of 6 RIOs throughout the country. and our coverage area is Texas and Oklahoma. So my job is to educate, train all things energy code through webinars, in person, and on-site field training for building officials, construction managers, contractors, trades, third-party verifiers, inspectors, and the like. So I receive daily phone calls and emails with questions related to enforcement compliance of the energy code. Some are from developers, some are from builders, and then others from inspectors and city officials. So I welcome any of those at any time. So just a little science class here. What is building science? What's it all about? Of course, it's one thing affects everything. How can we make things better? How one thing can make everything worse, but the whole house works together as a system. So identifying the envelope, sealing up penetrations in the envelope, and doing what we can to keep the conditioned air inside the house without having to overchange that air multiple times in a day. So I'm not going to read all of these, but how do you define it? This is kind of just coming directly off Wikipedia. But the very first one, building science traditionally includes the study of indoor thermal environment, indoor acoustic environment, indoor lighting environment, indoor air quality, and building resource usage, including the energy and building materials that's used to do that. So it's a study of how that works. So knowing the relationship and how these things fit together is the best way to approach an inspection as we go. As I was teaching my guys in the field and running through that with them on teaching them how to do the energy code. Sorry, I do have a chat here that says that the screen has changed. It's not full screen. Hopefully everyone can see that. If not, if someone can confirm that it's not being shown correctly, please let me know. So where does it start and where does it stop? So identifying the building's thermal envelope has been one of the key things to training somebody new on how to start an energy inspection. You guys, you won't have your eyes, you won't be able to see what you're looking at, but to identify where things start and stop is the very first thing that I try to teach my guys when I was with that third-party verifier on how to approach the home, approach the dwelling, approach the building. You've got to identify that and then start looking at the layers on what makes that up. So it refers to the layer of the home construction, keeps the interior warm, keeps it warm in the winter and cool in the summer. These layers can include the walls, the foundation, the windows. When using the thermal envelope is properly insulated and sealed, it can help reduce the amount of energy that's needed to heat and cool the home. We just talked about that a little bit, but it keeps the conditioned air inside longer to keep it from having to be overchanged and consuming more energy. In addition, a well-insulated thermal envelope can help improve the overall comfort of the home and reduce drafts and temperature fluctuations. So ensuring that a home has a proper functioning thermal envelope is an important factor for energy efficient and overall comfort. It also helps keeps out and mitigate moisture that moves into the building that can also change indoor comfort as well. So just a little bit on the code side of that. So air leakage in the code, it's defined the building thermal envelope shall be constructed to limit air leakage in accordance with the requirements of sections R 402.4.1 through 402.4.5. And with that part of it, we kind of go through that a little bit. We're not going to go through these in detail, but this is the kind of sections that it goes through. So it's the building thermal envelope as a whole, the installation table by component on how do you air seal that component, how do you insulate that component. It goes to the testing procedures and what the inspector and or person doing the test can and cannot do during the testing. It addresses the fireplaces that must have tight fitting doors or tight fitting dampers and or doors, and also must have makeup air for combustion. It also deals with air infiltration or fenestration air leakage, showing what the windows can leak up to and have to be certified for that under a certain testing procedure. Rooms containing fuel burning appliances, that's anytime you have a gas water heater, a gas furnace inside the conditioned space that needs to be handled properly in specific climate zones. And then recessed lighting, how are they sealed? How you have to address those and how they need to be insulated, be ICAT rated, so their insulation contact must be airtight. And then also the maximum fenestration U factor and SHGC throughout the envelope. So that kind of is what it goes through on what you need to follow, what's considered the air barrier. So when doing the air barrier inspection, Air leakage in the homes is increased. It can increase heating and cooling costs if it's not done correctly. It can cause moisture damage inside the walls. It allows for pollutants and debris to collect inside the interior walls, also providing openings for insect and rodents to enter the building if they're large enough. 5 essential components. It needs to be continuous. It needs to be no gaps, no cracks, no openings. It can be made of any impermeable air impermeable material. Must be rigid enough to support both sides from wind pressure. That's normally the case with residential because it's got cladding, it's got interior sheetrock, but it needs to hold up to those kind of pressures that are outside. It must also be durable and last the life of the building. And it also states repairable, accessible for damage. That's kind of not really the case when you can deal with the cladding on outside of the home. So type and placement of the air barrier systems, it can be multiple layers that make up this thermal envelope. It can include the insulation and a wrap, a liquid applied material, a solid material, a rigid material. It can be made up of multi-layers. So it can be also installed on the outside of the insulation or inside of the insulation layer, depending on your construction type. It must be continuous and fully aligned with the insulation layer. So a lot of times in multifamily indoor single or 2-story homes, that can get out of alignment and you see a separation of an air barrier and insulation. At all times, they must be continuous and aligned. And then can be made up of any air impermeable material. We talked about that. On these photos here, you see layers and layers that's being built to build up this thermal envelope. On the top right side, you can see a house wrap on a multifamily project. Lower left, you can see a liquid applied membrane that's happening over the dowel board that's on the outside or the GP glass board that's out there. That's another kind of forward innovative product that's being more and more accepted and more widely used in multifamily. And on the lower right, you kind of see a simplistic version of that in a home. Just behind the brick, you've got a house wrap over OSB on the cavities that are insulated. It looks like 2x6 framing on that part of it. So there's different ways of doing it, identifying it, breaking it down the layers, and finding out which one is the air barrier and what makes up all that is very important when the inspector's on site. Types of air barriers that we normally see. There's a few that we're going to go through here just in the construction that we see normally. House wrap, thermal ply, also known as T-ply, insulated boards or polyiso boards. OSB still being used from time to time. Then a makeup of that is a little bit called zip panels. That's what we see here in this photo. It's basically an OSB board with a sprayed membrane on the outside and an absolute airtight barrier if it's done right with air sealing of the joints. We have SIP panels, which is basically it's almost like just a insulation that's trapped in between 2 OSB boards, kind of like a foam board that's trapped in between 2 OSB boards to make up the framing member. And then we've got the liquid membranes that we saw a second ago on the photo before about how it was applied. To get into more specifics of it, we're going to go like thermoply and talk about, this is kind of some photos I took on a job site. It shows the correct placement of nailing patterns. So T-ply makes up a great air barrier and a drainage plane, but only if it's done correctly and following the manufacturer's instructions. So here we see 2 examples here that have been done correctly. On the left-hand side, we got the nailing patterns done correctly. They've used staples, but they followed the manufacturer specifications of every 3 inches it's been done on the verticals and the horizontal. It also appears to have all seams to be overlapped and stapled as well. There is 2 ways to do it. You can overlap it or you can butt the seams and tape it. This on the left-hand side was overlapped. And then on the right-hand side, the builder kind of went an extra mile. They added some air sealing products to the top of that. I think it's caulking that's done that. Any nail that's penetrated through that T-ply, they've added a bit of caulking on all those heads. Even on the brick ties that are on there, those bolts that are installed through there, they've actually added caulking on most of those as well. And as you can see, the seams are taped because they butted them together and didn't overlap them. You see Fortiflash on the junction between an opening on a door as well as where the T-ply hits from that. So that's important to see how that's done correctly. Here again, we see photos of just penetrations through that T-ply being taped with zip tape. This tape's kind of not meant for this application, but it turns out that it's great for this application because it's able to be stretched and cover those holes and seal up those penetrations. But as you can look closer here, if you can see this, it still is overlap. You only see one seam vertically that's been stapled, so that T-ply overlaps itself underneath. On the right-hand side, we've got seams that are butted together and fully taped. And then we've got caulking on all the nail heads. A lot of times that tape tends to fail before it gets cladding on it. That's another thing to look for. But if you pay closer attention, if you look at the horizontal seam that's at the top of that photo, these pieces are overlapped but not stapled because there's no framing members behind it. That leaves opening into the wall that allows for, it does create a good drainage plane and it follows the drainage plane down, but air can actually be sucked into that wall and pulled into that cavity. A blower door will find that on testing at final. So here's a kind of example of poorly installed T-ply. This is kind of what we see a lot, or what we did see a lot when I was out in the field. Is just staples or nails missing. So they've done a good job. Maybe they had a patch repair, but they've started putting the T-ply up. They've stapled it. They've tried to do a good job of sealing the seams, and then they miss staples. Like in the bottom left-hand picture, you see there's staples to the right side corner of that, and the further it gets into that corner, it's not stapled. A lot of times that happened under porches, around areas they feel like is not exposed to the outside elements, but they look at it from a drainage plane standpoint, not from also an air barrier. So having the trades understand this is acting as both drainage plane and air barrier, and it needs to follow manufacturer's instructions on sealing up all those joints and seams. It's ideal. It's crucial to getting a good air seal on that envelope. So another thing that's kind of bounced back a little bit, it used to be more commonly used, at least in DFW, and then it kind of had a resurgence when there was a shortage of T-ply, is house wrap. So it's light and easy to use. It's very cost effective. It's fast and easy for installation. It does control airflow very well. It controls water intrusion very well, but it's still breathable and allows for moisture vapor to pass through and allow homes to dry from the inside or to the outside as well. It also helps reduce home energy bills by allowing for the stoppage of airflow through there for infiltration. But again, it goes back to if it's done correctly. If it's patched together, if it's cut, patched multiple times, you got to make sure those seams are sealed. If they're not, that's going to allow for air and more bulk water to pull through. So overlapping these correctly, creating that drainage plane, and then doing it correctly to where bulk water can escape, but it actually seals up that member. Most of the time we see this overlapped over OSB, but I have witnessed a few builders, I think it was in the south part of Texas, that was using the T-ply, the house wrap as just its complete air barrier, and then they were just insulating against that. Not a great practice. I'm assuming it does meet both criteria of a drainage plane and a weather barrier, but it needs to have some kind of structure on the back of it for support. Sorry about that. Insulated panels, also polyiso. So that also is being used to up the R value of the wall structure. It's a great way and a great addition to add R value to that. But more importantly, it breaks the thermal bridge. So in order to keep heat transfer out of the home, if you're able to cover each stud with insulation and not allow for that heat to transfer through those studs, it's a great way to improve the overall R value of the inside of the home. Just because you have an R13 cavity and you have exposed studs to a T-ply, those thermal bridging allows for that overall R value to be diminished. Putting in an R3 board like we see here from Styrofoam or OXO, the OX boards, those allow for a further strength and improvement to adhere to the overall R value of 13 in the wall. So that's a great way to break that thermal bridge. But just like T-ply, the seams, the joints, they need to be taped correctly. The boards can be easily damaged. in the time of just moving them on the job site to installation. And a lot of times those repairs are overlooked. If the air pressure on the compressor isn't currently set, then each staple can actually push through that board and create holes everywhere that it's nailed. On the right-hand side, we can see a close-up shot of the actual staple pattern. It appeared to me that the compressor was set correctly. It did not puncture through that. But if they miss the studs or the framing members behind it, it can absolutely shoot its way through that board and come out the other side, leaving holes throughout the entire build envelope itself. So making sure those are done correctly. If it is not done that way, it needs to be taped. If they've punctured through it and created holes, need to make sure all the seams are sealed during the time of construction. Zip board is another air barrier that we see. Using it throughout the house as a whole, as we see to the left-hand side, this house was completely done with zip systems. It was done correctly. The tape on it was zip board tape. Looks like it was installed correctly with the applicator that the zip board systems actually sell and require for manufacturer specs to be done correctly. On the right-hand side, we see a mixture of zip and thermoply. That's okay in some areas, but if you have thermoply meeting zip, they are two different thicknesses of material. That leaves a joint that is different in thickness, and then overlapping that and trying to get a good seal between those is not ideal. So at the top of that zip board, that tape kind of overlapped a little bit and went down. It creates a good drainage plane, but if that tape doesn't adhere very well, it's an opening to the house itself. They didn't use it in junction with the running down the lengths of the home. They just used it in certain structural areas on the corners of the house. But butting those two dissimilar products need to be handled correctly for sure, and making sure that the zip tape is used and that the seams are sealed as best they can. The reason why a lot of this is important and a lot of things that we look at is how does moisture into the building? So we just went through the air barrier part of it, looked at a few things that kind of seem minuscule. It kind of seems picky and petty. You see punctures with nails. You see punctures with staples. You see little gaps that aren't stapled. You see overlaps that aren't stapled, and they leave gaps. Well, if you look at this, and it's all across the internet where you can do the research, but vapor diffusion is basically just moisture that moves through the building envelope. So you can't really stop it. You don't want to stop it, especially in this climate zone. You just kind of want to allow itself to dry in or allow itself to dry out. But if you see vapor diffusion, this is an example of a 4x8 sheet of sheetrock. You have an interior temperature of 70 degrees. The outside relative humidity is 40%. Just vapor diffusion alone moves about a third of quarter water per hour. So that doesn't seem like a whole lot, but it can move through that. It's not really going to damage products. You have the same board with the same conditions, and you have the accumulation of at least a 1-inch square hole, that can now turn into 30 quarts of water. So that's only 40% relative humidity. In Texas, we see that a lot, and then some, even more relative humidity higher than that in the 60s and 70%. So water can move through a lot faster if it's an open hole, as opposed to just pushing itself through with vapor. So just having holes, and that's about 100 times more important that you make sure these holes are sealed. Yes, it does seem petty. Yes, it does seem picky. But the accumulation of those, if you could cram those together and add them up, and they come to the size of a larger hole, like 1 inch, 2 inch, 6 inch. If you have that many holes in the envelope collectively, that's a lot of water that can be pushed through into a home. So what's an ideal range of moisture? I mean, it's all subject to interpretation with that. This is kind of what we find normally on the internet. Anywhere from 30 to 60% is the optimal Goldilocks range. Anything less than that and drier can still cause problems. So you've got dry area anywhere from 0 to 30% humidity, which is pretty dry. A lot of that happens in the wintertime. You get an increase of ozone creation. You get respiratory infections. You get viruses, bacteria. But then again, you go over the spectrum and you go 60% or higher. Now you also have increased bacteria, chemical interactions. Fungi can grow, mites, ozone, and then mold growth can happen as well with an increase of moisture. So you want that optimal range. Keeping that optimal range means, A, when your house is being built, make sure that all the seams, all the joints, all the holes, all the penetrations have been sealed to keep just corralling it just to be vapor pressure moving moisture in and out of the home, as opposed to anything larger than that pushing through the envelope. So judging the air barrier and looking at that, it's not just the exterior wall. So a lot of times overlooked is additional components that make up the thermal envelope. The air barrier, the insulation must be aligned and continuous. We talked about that a second ago. But that's in every component of the building that separates conditioned from unconditioned or conditioned from ambient spaces. As we can see in this photo here, this is a second floor that extends out over the ambient side. It must be insulated. The insulation should be pushed up against the floor above, conditioning the floor above, not being let down to where it's trying to condition an outside cladding. And then just inside that, on top of that first floor, top plate needs to also be blocked for that subfloor and not allow air to move through into that subfloor. A lot of times that was missing in what we see when we did our inspection. So other things and other areas to look for, though, is knee walls, band and rim joists, attic walls, demising walls, floors over unconditioned basement, floors over crawl space, floors over ambient, and then base plates. So base plates also a good place for air leakage, but with the increasing usage of townhomes and townhouses and increase in multifamily projects, compartmentalization and separation of each dwelling for energy has becoming increasingly more important. So just because it's a wall separating two conditioned spaces, a lot of people look at that as, well, it doesn't have to be insulated, and that's true, but air sealing needs to be handled the same as an exterior wall. So now having to do testing and compartmentalization testing, each one of those dwelling units need to test out as if it was a standalone freestanding house. There is not really in code, but it's coming in code, is basically using a sampling protocol where you don't have to test every single one of them. But if you handled each one of them correctly and they test out with most of them handling and passing, you can do a sampling protocol that doesn't allow you to have to do every single one. But keeping that separate, making sure that you identify the thermal boundary and the air barrier to create that. The seal gasket, I know this is mostly used in construction as a moisture stop. It stops wicking from a wet concrete to wick up through the base plate. But the seal gasket also in place stops air infiltration from underneath the base plate. Wood is not always perfect. Concrete is rarely ever perfect. So where the two meet, there's always gaps there. A lot of the builders, they do use poly seal on the inside on that gap. A lot of times it's either scraped off, but when the flooring is being installed, or if it has some expansion and contraction during construction, that poly seal can actually pop and it opens that gap again. But having that gasket placed there on all exterior walls, even including the garage wall, is ideal to have that that moisture stop installed for air intrusion. So it must be included. A lot of times garages are not looked at as exterior walls. They're looked at as an interior and or a garage separating wall, but that wall should always be handled as an exterior wall. When it comes to energy, it should be looked at as an exterior wall and handled properly with a proper air barrier and a gasket sealing the base plate. What we always did was, if they missed this gasket and didn't have it throughout the house, we usually asked them to lift the plastic drainage plane on the outside below where the cladding is going to go and actually caulk the outside of that. No, it didn't help with moisture stop from wet concrete, but there's no fix for that once the framing member gets added to the concrete itself. But it did help with air penetration and airflow through that base plate at time of testing at final. So checking that is key. But identifying the big holes in the envelope, we looked at the air barrier on the outside. We looked at kind of the separation between conditioned and unconditioned space, or the conditioned and outside area. But then over interior spaces, like over a conditioned space, the one on the left-hand side is subfloor openings over the garage. This one's handled correctly, but a lot of times they're not. They're forgotten. They're not looked at as important enough to seal. But you need, if the floor over garage isn't going to be insulated, then that's an unconditioned space that needs to be blocked off from anything that is a conditioned subfloor. which floors between conditioned spaces are unintentionally conditioned. They are part of that envelope. They do need to be blocked over the garage wall. And then on the right-hand side, it may be a little difficult to see. This was actually a dividing member, a TJI that separated a conditioned floor from an attic space. Where I was standing, I'm looking up into the attic. Those are service decking boards that you see there. Any penetrations through that TJI running from left to right needs to be sealed to keep anything from the unconditioned attic to be rushing into that subfloor and actually testing out on the blower door and or keeping comfort the same and not having that as a breathing hole into the attic. A lot of times those are overlooked as well. Another big holes to be found here. This is a media room. This is a false wall in front of a media wall. They're using it as mechanical chases for the flue pipes from water heaters downstairs in the garage. They're also using it to run Cat5 and internet drops and HDMI tubes, but they've left the whole entire top wide open. So if you leave the whole entire top wide open, you have to decide as an inspector, A, where are they going to insulate? B, are they going to cap the top? And C, where is the air barrier going to be placed? So remember, we talked about again, has to be continuous and aligned at all times. If they insulate the exterior wall, that's fine, but they're going to have to T-ply in front of that insulation on that back wall, and they're still going to have to cap the top to keep the front of that wall, the false wall, from breathing air down through the attic during a blower door test. If they insulate the front wall and make that the envelope, that's fine, but now you have to T-ply the back of that and air seal it, as well as insulate and add sheetrock on the front. At all times, we'll talk about this more in a second, but at all times, insulation must be trapped within a 6-side. As we were talking about a second ago, just opening of the top walls, media walls. This doesn't always just happen in the media rooms. This can happen anywhere where they're trying to have a chase, either duct chase or mechanical piping chase. These things need to be blocked and sealed at the top, at the back. Identify where the thermal envelope is, making sure that that insulation is sealed within a 6-sided encapsulation, either in the front of this wall or the back of this wall, and then that needs to be decided. Sorry, I hope this is back to normal. My apologies for that. Another thing here that we look at is things that are hiding in plain sight. So on the left-hand side and the right-hand side, both these pictures are the same thing, but just from different angles. So if you look on it from the left, I'm standing in a master bath closet, towel closet, looking up, and it looks like the sheetrock's going to go all the way to the top plate, the very top plate. That's all going to be interior wall. If you look at it from the backside angle of that, there's actually a vault that was built into the master, probably to match the vault on the other side of the room. So for aesthetic reasons, they built a vault here. It also helped them run ducts through there. But if you look closely enough now, it is wide open to the wall that's on the interior side of that. So that's also going to have to be trapped in a 6-sided encapsulation. It's going to have to be insulated, T-plied and sealed on the attic side, as well as insulated and sheetrocked on the inside. But just seeing it from a different perspective can give you an idea as to what needs to be done at this point, how this needs to be handled, and how it needs to be addressed. So open-ended floors over garage. This is a lot of times what I saw this a lot. It's basically either a media room and or a foyer that pushes out over a garage. It's a second floor that extends over the garage just shortly, 1.5, 2 feet most. But during that, you've actually got to make sure that that is also 6-sided encapsulated. Yep, Tom, you're correct. You put on there, what about the pinch duct? That absolutely also should be called out as well. But the flooring itself, so that insulation, on top of that top plate that's going over from the garage to the interior, needs to also have blocking there and need to be sealed. There's polyseal at the duct, around the duct that's going through that. So when I look through that, that was blocked. But the insulation cannot be exposed to an unconditioned attic over the garage. So between all of these floor joists or ceiling joists of the garage, all need to be blocked. And it's going to be sheetrock from the bottom and blocked at the end and OSB at the top. So that's 6-sided encapsulated. If it's left open, this insulation will have air move right through it. It will be a hot spot on the second floor, and it will actually show up real hot on an IR camera during the summer. So that's got to be blocked off as well. So the framers don't particularly like doing that. A lot of times there's duct work that move through those flooring systems. It's very difficult kind of for them to cut and put those through there, but using T-ply, pieces of TJI, or just solid wood is what's needed here to get those things sealed. Some more subfloor openings over the garage. This kind of comes from the PNNL website. They have good and bad, thumbs up, thumbs down on components on how it's done correctly. On the left-hand side, you see basically floor joist cavities being wide open from the garage into the home itself. All of that has to be blocked like it is to the right-hand side. That blocking should meet at the top of the garage wall as close to it as you can. A lot of times if the TJIs are running parallel with the garage wall, just choosing one side or the other that's closest and air sealing any penetrations there is usually sufficient enough. But if it runs perpendicular, now every single space between those floor joists or TJIs are going to have to be blocked and sealed to keep air from moving into the conditioned space subfloor from the garage itself. So that's got to be done as well. And then we don't see this a lot. I think there's more in South Texas. You can kind of see some of this, but raised flooring not being blocked. Some of the houses, they actually will raise the flooring off, put mechanicals, electrical, piping, plumbing, all that's through there. The one on the right-hand side is the correct way to frame it. It's got a TJI put there, and it's actually attached to that framing part of it and holding up the wall, and or just some OSB that's been cut for that. But the one on the left-hand side is going to have to be blocked and sealed. You can't leave that open from the garage itself. So code doesn't spell it out the way Energy Star does, but garage is considered an unconditioned space by code. Energy Star sees it as contaminant source. So code's starting to come around to that same thing, saying it's pollutants, it's contaminants. You need to air seal the house and be separated from the garage. The more resiliency and sustainability and things that get pushed into objectives, that's being more the leading cause than just air. But Energy Star also says contaminants cannot breathe its way into the home. And don't forget about all the ceiling penetration. So when you have an unconditioned attic or a vented attic, the ceiling sheetrock is the envelope's air barrier. All penetrations through the ceiling must be sealed. So most of these that are listed can be sealed with polyseal or caulking, but sprinklers should also be sealed per the manufacturer's instructions. I know this is a bit controversial. There's a ton of opinions out there, whether to seal, whether not to seal. The escutcheons, which you see here, this is a gray, that metal gray escutcheon there, can be sealed to the drywall opening without compromising the safety or proper operation of the sprinklers. But most of the time that still requires the fire marshal or manufacturer to sign off. So there's usually pushback on that. So according to the National Fire and Sprinkler Association back in 2020, they basically said the same thing. This can be done, but needs to follow manufacturer specifications. If it's an escutcheon that's made of plastic, if you use the wrong sealant, it can deteriorate the plastic. It can cause problems with the operation. Most of what I saw in multifamily and single family has metal escutcheon housings. Those can be sealed to the opening. Most of the time when the sheetrockers cut those openings, they're bigger than what they should be. Just like with this is through a piece of wood, but it's resembling the same thing as what we see with sheetrock. It's cut very big. The cap itself goes over it, but is not airtight. There's no gaskets on the beauty cap that's on the bottom. So we've asked for those things to be sealed. Usually we have to go back to the fire marshal or the city, the chief building inspector, and say, how are we going to do this? But additional air sealing things that are also required are the recessed can lights. Most of those come with gaskets, but if the gaskets are thrown away or not done properly, that can leak. All electrical boxes like CO and smoke, security, lighting, cameras, anything that penetrates through the ceiling needs to be sealed. HVAC boots, so around all supply and return boots before the grill goes up, Where that boot penetrates through the sheetrock must be sealed. All ceiling fan boxes, same thing. Exhaust fan housings for bath and kitchen also need to be sealed. Those are still leaky because of the way they're manufactured, but it needs to be air sealed on the opening around the sheetrock. And then, as we just talked about a second ago, sprinkler cans, yes, they can be sealed if you follow manufacturer specifications. If the fire marshal or CBO basically says that's a no-go, then you have to follow that recommendation. The hardest part is then how are we going to pass a blower door? You got to do additional measures to actually get there, because having openings, multiple openings like this for sprinkler holes is going to cause it to be very difficult to hit a low ACH on the house. So behind tubs and showers on exterior walls. Used to just be an Energy Star thing. It's now a code thing. It's got to be blocked and sealed. Left-hand side, you see a tub. You see the insulation below the tub against that exterior wall. It now must have an air barrier installed and sealed. So anything that normally would have sheetrock, if the item or appliance was not there, if it was normally going to have sheetrock, but now they put something there and sheetrock is not going to cover it, must still have an air barrier installed over the insulation. So doing it after the fact, like we see on the left-hand side, tub is installed, insulation's exposed, getting an air barrier there now and getting it sealed is going to be very difficult. Planning ahead in the framing stage, having pre-insulation dropped and air barriers installed, like you see on the right-hand side, before the appliance gets put in, or a tub or a shower enclosure, is the best way to handle it. That even includes when a tub or shower is installed on the garage wall, you still got to have an air barrier separating the garage wall insulation from the interior side. It has to be air sealed. So doing that pre-tub or shower drop is the best way to handle that, as opposed to trying to do it after the fact. It needs to be blocked from the inside. And after talking about all the air barrier sealing and how that goes, how are we confirming what that's actually done correctly? For one, we do the inspections. Two, we do a test at the end. So blower door testing. There are different ways of doing it. There's optional test methods. There's single point, which only one measurement's taken. It's the fastest. It's less accurate. Then you've got multi-point tests. It actually takes a measurement of 10 different steps at 10 different pressures, and then it calculates the average. It takes longer, but it's more accurate. But a blower door, to popular belief and contrary to popular belief, a lot of people think the blower door can pinpoint where problems are. That's not what a blower door does. A blower door measures air infiltration throughout the house. It simulates air hitting the house from all sides, multiple directions at the same time. That's not reality. It never really happens. But this is a standard pressure test that has to be done on all new construction to confirm the air barrier is sufficient enough to pass the test. Doesn't pinpoint where it is. So if you get to a final, blower door is failing, it's very difficult to say, I know exactly where this is coming from. That's not what blower door is about. It's about finding out where you actually stand on compliant. So when doing the blower door, basically there are certain things that the inspector can do. So testing and verifying code compliance is what it's used for. Sometimes it's part of an energy audit. We're talking about new construction. It also can be done for remodeling and renovations. And then it's tested during new construction, of course, and then using blower door assist for air sealing. So if you're running it in conjunction where you're trying to air seal a house, you can do that. But most new constructions don't go that far. A lot of times they're air sealed properly enough unless something went wrong to make sure that it's actually done. I'm not going to read all of that slide. That kind of just goes through the compliance testing. But when you do the testing, when the rater or inspector does the testing, you can't really tape up supply and returns. You can't tape up the openings around sheetrock penetrations like sprinklers. You can't tape around bath fans. You have to leave those things as is. It has to test out as if the homeowner was occupying the home and how it's going to perform on an everyday basis. You can't seal things up to manipulate the test. That's not what the test is for. So on to the insulation side of it. So just a little brief history, just kind of the way insulation works. So insulation basically works by resisting heat flow or the transfer of heat flow through the component or through the building material. So either from the outside in or the inside out, its power comes from the ability to trap air. So as long as it's fluffy and it's nice, it's got air pockets in there that resist heat transfer through the material. But if it's crushed, if it's compressed, if it's devoid and it's not there, then it doesn't work very good. Heat is able to transfer through more of a solid material if the pockets of air aren't there. Once it reaches a stopping point, it re-radiates. So if we look at the picture here, the sun's hitting the roof, it's heating it up by radiant heat. That radiant heat travels by conductivity through all the framing members. Once it hits a stopping point, it re-radiates itself into the attic, and then due to radiant and temperature in the air, it hits the surface of the insulation and it starts to travel through the insulation and through the minute pockets of air trapped in it's trapped in the insulation. Then it hits the sheetrock. Then it starts the process over again. Now it's conduction and it's pushing through the sheetrock, and now it re-radiates itself inside the home. If you can use at any point a way to slow that down, that's what insulation is all about. You slow down the heat transfer through that. That's not just for insulation in the attic, that's for all components of the building. So as long as the insulation is installed properly, and it's also within a 6-sided encapsulation, and you've stopped air moving, because once air is introduced into the insulation, the R value greatly diminishes. So the reason you don't cap, and I had this question asked last week, the reason you don't cap insulation in the attic is another reason why we have such high depths of insulation in the attic. You can't really cap it, and no one's really going to want to put a cap on it. So they basically just, the deeper it goes, the more depth of insulation, the longer it has to travel, the less likely it is that that heat's going to hit the sheetrock at a high temperature to then re-radiate it into the house itself. So that's the only component really that's not trapped in a 6-sided encapsulation, but then they've doubled or even tripled the depth of that to overcome the fact of it's not being trapped. So just a little bit about insulation and looking at it is gaps. Gaps and compressions. So the important part of the inspector is to basically verify that all insulation meets manufacturer specifications, also known as grade 1. The term grading is not used in the energy code language, but instead the code references the manufacturer's instructions for installation. All manufacturer instructions that I've read basically describes the definition of their installation process as the same as a definition of grade 1. So whether grading is used or not, the inspector must properly define how good the installation was done. So things to verify is voids, gaps, compressions. A higher percentage of these basically lowers the effective R value throughout the building envelope. It's kind of like a domino effect. So a poor job of sealing the air holes in the air barrier, having a poor job of installing the insulation, or you've got a lot of compressions. Then you add windows and doors, and you basically cut holes in the envelope. And then you kind of lose the whole value of why you're insulating that wall to begin with. Not really. I mean, there is a little bit of heat transfer that's slowed down, but when you've got holes in the walls, you've got bad insulation, you've got holes that are in the air barrier, and that heat is going to transfer through really quick. The important part of that, and what a lot of people don't understand, is the more compressions and the more gaps that you have, you start to move the condensation point within the wall. So you see on the left-hand side, you see a gap in the insulation. If heat's hitting the outside of that and you've actively doing conditioning inside, let's say the homeowner's keeping it at 78 degrees, or not 78, 72 degrees or 70 degrees, it's very cold. If 98 to 100 degrees is able to transfer through that wall quickly and hit that cold surface of the sheetrock, that's where condensation is going to happen. So having a complete devoid of gaps is what you really want to look for. Having compressions is almost as bad because you're still moving that condensation point inside that interior of the wall, and then bad things can happen due to that. Getting called back from a builder or a homeowner and asking them to run a blower door and a duct blaster because they're having either humidity issues or they're having condensation issues inside the home, or even unfortunately mold inside of it, you come up with an inconclusive findings. It's not usually due to air leakage. It's more likely due to voids or gaps in the compression that's allowing for the condensation to move into the house itself. So, or at least up to the sheetrock wall, allowing for that condensation point to happen. Another way to look at insulation grading, it's not as easy to be defined. If you look on the internet, there's different ways to look at it. A lot of times it's best to split. you've got a specific criteria for gaps, and you've got a specific criteria for compressions. So looking at a grade 1, it's minimal gaps. And then you've got compressions, you can be up to 2% of that wall is compressed. And then all the way up to grade 3, you've got more than 2 to 5 on gaps, and then more than 10% of that wall is compressed. But as you see here, the more you go into components like walls, rim joists, band joists, floors between spaces, ceilings, and then floors over outside ambient air, you kind of lose that. You can't be grade 2, you can't be grade 3 because it's extremely detrimental to heat transfer into the envelope. What you really need is a grade 1 install on all of those, and not only a grade 1 install, but the insulation has to be placed correctly. So if it's over ambient or over the garage, the insulation has to be pushed against the conditioned floor above, not left to be insulating the cladding over a porch area. So another way to look at it, kind of a lot of people are more visual on what does that look like. So grading of the insulation, you see this is kind of a gap map. So grade 1, grade 2, grade 3, you see kind of a varying of more gaps to the right showing grade 3. But doing the gaps of that is easy to see, but it's not just the insulation itself when you're looking at it from the front. It also includes around wires and piping, behind ladder blocks, behind cabinet blocking, at all exterior corners, behind all T-wall intersections, behind exterior wall electrical boxes, band and rim joists, and then floors over garage and floor over ambient spaces. So just because you look like it looks like there's no gaps in the insulation, but you've put your hand behind the blocking or behind the wiring or behind the piping, and there's nothing there, that's gaps. And you start adding those gaps up, and it greatly starts to diminish to a grade 2, grade 3, or even beyond. So if you get to that point where you're a grade 3, 9 times out of 10, that's not acceptable, especially if you reran that through an energy model and put grade 3, it's diminished so to the point where it will not pass an energy model. So kind of a quick synopsis of just impacts of that. If you have an R13 wall and you've got only 2% gaps, the overall R value of that is roughly about an R11. And then you go further down from that, 4% gaps, which doesn't sound like a lot, now runs that overall to about an R9. And then again, you punch holes in that and you call it windows and doors, and the overall R value of that wall now diminishes to below 6, 7, 8, sometimes less if it's not installed correctly. It gets to the point where that wall alone is going to be causing a problem for heat gain and heat losses throughout the home. And just another, speaking of just the 6-sided encapsulated knee walls, exterior walls see a temperature difference varying from highs to lows, but no part of the country really sees 130, 140, or even 160 plus difference, but knee walls do. So these are widely overlooked and considered an interior separation wall, just separating unconditioned spaces. However, these specific areas are subject to the highest temperature differentials of any component throughout the building envelope. So these should be specifically addressed and verified that all insulation is 6-sided encapsulated. It's sealed on the backside. The insulation is devoid of gaps. It has very minimal compressions to it at all, just to be able to uphold the R value of that wall and not have heat transfer through that wall. So anything less greatly increases that heat load and is able to enter into the space by re-radiating into the space. Most of the times these are not really high enough, or these are high enough on the wall that homeowners won't see it as a complaint issue because they're not standing next to it. But over time, it can heat up that space, causing for the adjustment of the HVAC for more conditioning. And then that's just leading to more energy usage of the building itself. And then types of insulation, we'll quickly kind of go through this part of it, but we got bats, we got wall blow, we got cellulose, either in a wet or dry application. We have open cell foam and closed cell foam. On this graph here, it's kind of hard to see, it's blurry because it was blown up. It basically shows an R19 bat on the right-hand side. Cellulose has a little bit of a higher R value in the same cavity, an R21. Open cell, a little higher than that, between 22 and 23. And then closed cell in the same cavity can be about 32. So it's rare to see closed cell because it's so costly, but open cell is becoming more and more common. So wall and bat blow, just got to look at this and identify the deficiencies in that part of it. It's harder to do when it's blown in, but pros of both of these: basically cost effective, easy to use, quick of installation, easy to get corrected if you're going to do some corrections for that. The con basically is it suffers poorly on performance if it's not installed correctly. can also conduct heat through adjacent materials, and then fiberglass fibers can be an irritant. But if the insulation on the lower right-hand corner of the picture there, if the weight and density of that insulation is not correct, that will settle over time and leave gaps above that wall. It's very hard to determine, is it the right density? My team always pushed on it. If it pushed in and left a handprint, it's probably not a very dense blow. If it pushed in and rebounded a little bit, or it was really hard to push in, then it was probably a dense pack. A lot of installers out there have learned to dense pack that, and it's an R15 wall inside a 3.5-inch cavity, which is ideal and great. But at the end of the day, they also need to sign off and have a certificate posted in the wall in the house at a pre-drywall stage to confirm that that's the R value that's been installed. Cellulose wall blow, both dry and wet applications. So the cons is added comfort as well as sound reduction for that. It's got a pest deterrent in it. It's also got a fire retardant that's in it, and it uses less energy just to make it. It's ground up newspaper and has a borate treatment that's been sprayed in it. The cons is basically there's some installation challenges. So someone's really got to kind of know what they're doing, and it can settle over time. And it gets less performance if it gets wet. So if it's a high moisture area, you may not want to use that, because once it gets wet, it kind of loses its overall R value. But if you see on the top left, this is sprayed wet and then shaved off at the stud edge. And on the right-hand side, lower right, they actually have netted and blown that in as well. So getting full coverage with that. Spray foam wall insulation, it's getting more and more common to have spray foam that we see out there. Pros, it's the highest R value per inch. It can be applied to any surface. It can also eliminate any need for a separate air barrier or vapor barrier. The cons is you got installation can produce toxic gases, not as much in open cell as closed cell, creates a mess on site, and also through unsealed joints and openings, requires a specialized contractor, and it's more expensive material. That's becoming more and less of an issue down the road, because those are just insulators that do bats have now learned how to use foam. They've got a foam rig, they know how to do it. But if it's not installed correctly, and there's a big a chance that the installers are trying to save labor and time. So if you spray foam correctly and you fully fill the cavity, you got to go back and shave off the cavity, and that way it's got full depth insulation on all of it. But if they learn how to do it correct, if they learn to where they can spray less in the cavity and not have to shave as much, it saves on time. But that's kind of you have to look at what's the overall R value. In the lower right-hand corner, you see this was just a simple meat skewer that had tape on it. What we did was stick it in the foam. If the 3.5-inch cavity was anywhere within that orange tape, it was adequate for insulation install. If a 5.5-inch cavity or roof rafter actually hit anywhere within that black, then it actually met for our compliance. So an overall average of the right insulation was done. So we moved on from there. But as you see, the divots and the decreased insulation between cavities, if it's too much of a degree decrease and there's not enough insulation in there, the overall R value is affected, and that should be called out and should be resprayed to have that done with the overall R value. So kind of some tricks of the trade. I use this a lot in presentations. I just think it was kind of humorous to see it done, but the framer framed it incorrectly on this short wall over a fireplace. So the installer of the insulation, instead of telling anyone or notifying them that it needed to be reframed, they basically just ripped an R13 bat in half. I think that was a 15, but they ripped it in half, and then they just stuck it in that cavity. It's only 1.5 inches in depth. So half of that is basically not even adequate enough for an attic wall like this was, separating an unconditioned attic from the interior wall. It needed to be called out and needed to be reframed to hold an R13 bat in this. But this is something that from the surface on the left-hand side, if you were just doing an inspection and saw R15, looks like it's meeting the intent, meeting the requirement of code. Under further investigation, you pull that back with a little stick or anything you find there in the job site, you can clearly see that it was split in half and not done accurately. Attic insulation. So all attic insulation installed in the envelope must have an R value identification mark on anything larger than 12 inches or wider per code. Blown in or sprayed roof and ceiling insulation must have depth markers installed. one every 300 square feet of that attic space. The markers must be affixed to a truss or joist. The thickness and R value must be indicated on the certificate posted by the installer of spray foam and below attic insulation and posted in the attic itself. Each marker must face the attic opening, and then installation materials must be installed where the manufacturer's R value is readily observable. That's kind of for flat ceilings. If you're doing bats and you've got to see it from the floor, have the R value readily available. Here we see a picture of the yard markers being stuck up. They're not attached to anything. Probably by the time humidity hits that, they're all going to be laying down in the insulation, not observable for inspection. It looks like they propped them up with something, so that was still able to see those at a final, but they should be affixed to something to where they don't actually sag during construction to know that the insulation has been blown properly. So spray foam under the roof decking. So most roof framing around that we see is 2x6, which is only 5.5 inches in depth. So a lot of this has been used in the way they do it in residential. The overall R value of that is about, if you multiplied 3.5 inch per inch, 3.5 per inch of foam, multiply it times 5.5, you only come up to about a 19.25. But a lot of times you look at, well, if you're in the climate zone that's requiring 38 or 49 in the attic insulation, how is that actually happening? How is that okay? How is that getting through? It comes down to the energy model itself. So from when I was doing the inspections, I know the engineering department basically stated that anything that was foam, they had to use the ERI calculation pathway, because doing performance path did not have the right calculation or engine calculations to actually understand foam. In other words, it would fail the house if it didn't say R38. ERI would look at it differently. It allows for the trade-offs, and the calculations were done correctly. So if you're a plan reviewer, pay close attention to the permit document. So if they're using performance and they're using foam encapsulation, look specifically at the value listed for ceilings. Because if it says 38, that's going to be wrong, because they're not going to have enough depth in their rafters to put 38 with open cells. It's going to be a 20 to 21 in those rafters, which isn't incorrect, but your modeling software needs to state that it's a passable and not just throwing a number in to get it through code. So just a little bit about more requirements. Just protecting the insulation from wind washing is the eave baffle. So any air permeable insulation in vented attics must have a baffle installed adjacent to the soffits. Now the new code, I believe 2021, is stating that it's not just adjacent, it's got to be in every cavity in the ceiling, because they know that wind washes through there regardless of whether there's a vent or not. Baffles shall be maintain a net-free opening for air to move through the attic itself. It must extend over the top of the attic insulation. They can be almost any solid material. Baffles need to be installed on the outer edge of the exterior wall top plate. So if you see on the lower left where the thumb's going down, that's in the front on the top plate. That's incorrect. You need to have it to where it's on the right-hand photo there, where it's actually stapled to the back side of the top plate to allow for a full depth of insulation to reach the exterior top plate and continue that thermal envelope all the way around the outside of the house. So it needs to be installed correctly. A lot of times installers will just roll up a bat and stuff it in there over that that baffle, and then keep that baffle in place by a rolled up piece of insulation, which is fine as long as the top plate itself is being insulated. So access hatches and doors. So vertical and horizontal access hatches need to be weather stripped. Access to prevent damage or compression of the insulation shall be provided. If any loose filled insulation, a wood frame or equivalent baffle shall be installed and to prevent any of it from spilling into the living spaces. And then the baffle or equivalent shall be provided a permanent means of maintaining the R value of the loose fill insulation. In other words, protect it as much that can be done. On the right-hand side, you see a bat that's actually attached to the top of the scuttle hole cover. That's the right way to do it. And then you've got framing members all the way around the opening that's actually holding the insulation in place and covering those top plates. We reiterate again, if any loose fill insulation, wood frame or equivalent baffle shall be installed to prevent spilling of insulation into the attic space. This is kind of not really meeting the intent. If you can see that, that's a lattice work of polyfoam. I think it probably would not fall out, but as you see, it's also tapering down to the framing member of the opening, and that's not the intent of the code. It needs to have blocking to where the insulation is at its full depth, all the way to the edge of the top plate that's surrounding the opening of that attic. So that must be done to maintain the R value throughout the attic. Tapering that, you're lessening the overall R value of the attic itself. Another shot of the correct way to dam up the insulation. Can be made of any solid material, must extend to the full height of the insulation, and should surround any openings to the attic. So if you're separating a garage wall or a garage attic that's uninsulated from a attic below, so instead of tapering that down and leaving the top plate exposed, having this vertical kind of knee wall look to it, just damming up the insulation and being able to blow full depth insulation all the way to the top plate is what code is looking for. Not yet common, but basically is buried ducts that's allowed now in the 2018 and 2021 code and beyond is doing buried ducts. So if you start seeing anyone that does this, there are different ways to do it per climate zone. It's all dependent on the climate zone as to how you have to insulate them, where they have to be placed on the attic floor, and how you have to insulate over the top. So the three different ones that you see here. So we're looking at this part of it. Basically, it's all supply and return ducts must be R8. At all points along each duct, the sum of the insulation R value against it and against the bottom of it shall be not less than R19. That includes the duct, not including the duct insulation. So if it's R8, you can't add 8 more and then call it 16, and then you do a little 2 more, and then you do, okay, well, that's 19, or that's 18, or it's got to be not including of the duct insulation itself. In climate zones 1, 2, and 3, the supply duct shall be completely buried within the insulation and then insulated to an R value of not less than 13. So the last one here puts the ducts in direct contact with the conditioned space, being that's climate zone 1, 2, and 3 are predominantly for cooling seasons, basically burying them completely, lessening the chance of heat gain from an attic. So if you do that and you do see that, that is now considering the ducts in conditioned space. And so in 2018, they didn't have to be duct tested if they're considered in conditioned space. 2021 and beyond, you're actually going to have to duct test it regardless of location, even if it's within a conditioned space or encapsulated attic. So the last thing I hear that I have is a great resource. It's a component by component guide from Building America Solutions Center. That's basically by the Office of Energy Efficiency and Renewable Energy. You can basically select it by the building components, or you can go to an A to a Z guide, and it shows proper definition, scope of work, and it shows training pictures on, as we seen a minute ago with the thumbs up or thumb down, it actually shows good and bad photos of how it should be done. And that's good with training and field training as well. So that's it for today's presentations. Feel free to contact me at any point with comments, questions, or to schedule me or any of my peers with SPEAR for an in-person presentation or field training. Also, be sure to use the survey to provide feedback to me on what topics you'd like to see covered in future webinars. I apologize for the technical difficulties we had before when it split up. If you haven't already, be sure and sign up and register for our energy newsletter on our website. That way you'll be notified of the next date and time of our next webinars. Just click the link at the bottom left of our landing page, and it basically says join our newsletters. You can select the CELC website for the city legislation or local governments webinars, as well as the energy side of it as well. So we're going to go through and see if there's any questions that are here. Nope. If you've got any questions, I'll remain on here for a few more minutes. Again, thanks for y'all's time. I appreciate it. I know for some people this may be mostly elementary information, but I know a lot of times there's ways to just kind of refresh what you thought you knew in the field and you forgot. So Gerald actually says, please repeat the way that we'll get certificates. So shortly after this webinar, you'll actually receive an email, a survey email from Kathy Lawrence. That survey needs to be completed and filled out. I think there's 5 or 6 questions to that. Fill that out, send it back to her. Once she receives that, then she's going to send you a course completion certification. Under that certification, you'll have a course ID number that you can use to turn into ICC when you use that to report for your CEUs. Any other questions? And again, please feel free to contact me at any points. Comments. We're starting to build our presentations going forward. We have some upcoming presentations with some guests that'll be speaking. But I really like to put these on where we actually get down and dirty and actually talk about field verification. So what about using EPS sandwich between roofing deck and roof materials? Yeah, that can be done for sure. That's we don't really see that a lot. There's a lot of you'd have to kind of really have the technique and know how to do that to handle it correctly. But yes, that's a good way to do it as well. Any other questions for that? Appreciate all the thumbs up and accolades here. Thank y'all very much. Let's see. Was the polycell lattice something we've seen multiple times? No, that was just once that I saw that. Thanks, Dylan, for that question. That was just once that we saw that. I think someone just had too much time on their hand. George says, is there any way to get a copy of the PowerPoint? I can email it to you. It's tough because they're usually bigger and they won't email. I can send you a share link and drop that in there. If you want to email me, I can do that and actually share that with you. Otherwise, there is the webinar will be reposted on our YouTube channel. All right, if there's no further questions, I'll end it here. Again, thanks for y'all's time. I appreciate it very much. Have a great rest of your week.